Hello guys, this is Ricky Electronic Marine. I used to fix electronics for a job, marine electronics, GPS, autopilots and so on in the lab. And today we're gonna see a couple of things about BMS, especially for lithium iron phosphate cells. The main argument of this video it's one Chinese BMS and that's this one that I'm currently testing. But before going into that, let's just speak a little bit about what else it's going on around with BMSs. Now, there are a couple of types of BMSs. We'll start from the cheapest one there is around. This is a schematic. It seems really complicated, but I'll try to break it into parts. That way you can understand that physically it's built like this. It goes like 3 or the whole board. Now, what's inside the BMS? First of all, in this one we have a part that is this one. That is the balancing part. The batteries, the elements are here between this one, this one, this one, this one, like this. These are the batteries inside, and it's a 4-cell BMS that handles 4 cells, so it will be good for a 12-volt application. Small note, these serial numbers here for these chips are for lithium ion cells, but there are the equivalents that are doing lithium iron phosphate also. Now, depending on the type of the small chip, every one of them, every electronic component has a data sheet. That's a paper where you can find all the characteristics, what is done, what it is. For example, even this one is SLS 2302 has its own data sheet. Generally the resistors don't have data sheets, but all other electronic components have a data sheet where you'll find everything written about what it is, what are the characteristics and so on. Now, in this type of BMS, we'll take half of the part. This is the balancing part. It's a passive balancing. It's like you take a light bulb and you put it only one cell on one cell. When the voltage over the cell exceeds a certain value that's already programmed in the chip, let's say, I don't know, when the voltage gets to 4.2 volts, we'll just attach 2 resistors and will dissipate power, will lose power through those 2 resistors. That way, it's a way to deny a higher voltage on a cell, and that's a passive balancing type. So you have a small part. This is a simplified scheme. You have one element that's connected with the other down, with another one on the top side, and they're all in series. And when the voltage over this element gets to a certain limit that's programmed in the chip, or you can set it with an external resistor and so on, we'll just open the passage to this Mosfet. It's like putting a switch. Will turn on and will start losing a bit of power through resistors and through heat, and that way it lowers the voltage of a cell. Is the stupidest let's say way of balancing the cells and so on, and the cheapest one. It costs like 5 cents one, and all the parts are like, I don't know, maximum 50 cents. Then there's the monitoring part, and those small chips are reading each one of them the voltage on one cell. So the BMS, it's made in 4 cells and 4 different blocks. One that's handling the balancing, one that's handling the protection part. When the voltage exceeds 4.2 volt, will give a signal that will give a signal to a transistor, to a common line that's common. So whatever of the 4 elements will start going over or under will give a signal. One is for over voltage, one is for under voltage. So when it gives the signal, we'll just close and don't permit the passage to the current in the MOSFETs. These MOSFETs are like a switch on the other side. So when they receive current is like when you put your finger over it, so it'll have a positive voltage on it, will be closed. When you took out the finger, you took out the voltage from the gate of the MOSFET, will open and will not pass the current through the MOSFET. So these ones are the ones that are sensing the voltage on every cell, and then they're combined on two buses, two main buses. This is one bus that's going over the charge part, and one it's over the discharge part. The one over the discharge part will just turn everything off when the voltage goes under a certain limit. Now the protection part, the overcurrent and short circuit protection, it's made by those two resistors that are a shunt practically. Over here are two smaller resistors, but it's the same thing as a shunt, that at the passage of the current through the shunt will give you a voltage on the two sides of the shunt. You'll find it on every battery monitor, every ammeter. This is a Chinese battery monitor, so you have the shunt. And the shunt is responsible for the overcurrent protection. In this case, from the shunt, the voltage goes through these resistors to this pin, number 2 of the chip, and the chip will switch everything off. So all the big power protection part, it's handled by this small chip. Altogether it costs like I don't know, a couple of cents. Physically you can see them here. This is the balancing part, when you find the two resistors in parallel. Those are the leads for the balancing part, and then you'll have the B, P, and so on, the connection of the batteries. And this is the balancing part. You'll find the resistors, the transistor, that's this one, the MOSFET, and the small chip that does the balancing part. On the other side, you'll find 4 of these chips, that are those 4 transistors, and other 4 that's one and the other, and then you have the MOSFETs and the shunt. These are the main parts of a really cheapy BMS that you can have around. Now there are other type of BMSs where everything is handled by an integrated circuit and has all the functions inside. This is another version of BMS with a Chinese, I don't know the brand, is the first time I hear about it, that controls everything in the cells. The difference between this one and the other one is that here it sends the cells, and at least when it does the balancing part, that will be always through a resistor and a MOSFET and a switch, at least it can sense the difference between one cell and the other. Meanwhile, the other one will wait until a cell gets to a certain voltage. Let's say this one gets to 4.2 volt, will start the balancing, and this one, if it is at 4 volt, will not be balancing. This one instead, it senses, so you can set a threshold, let's say, I don't know, 50 millivolts difference between one of the cells and the others. Then another thing that you find in this version of BMS is that you have an NTC, that is a resistor that changes the value with temperature, so is used as a temperature sensor. Physically, in this circuit, although it was written in the seller's ad that it's present temperature protection, you can see NTC not connected. The resistor that serves as a calibration for the NTC threshold and what temperature goes, that's one of these air temp, I think it is. The resistor is not present, so this one doesn't have a temperature control. On the small board there are the LEDs also. It can also be used for 4 cells. There are many ways to connect this one. We can see the air sense, that's the shunt resistor, it's by 4. You can see charging port, GH minus, and the discharge port, that's the P and the C. Also, like the other one, on the output it has 2 MOSFETs. Now what's happening in this case? In this case, when you are charging and maybe the discharge port it's turned off, when the batteries are getting low, one of the elements is low, the voltage of the whole pack is low, will close this one, will not permit the current to pass from the battery towards your users, the loads on board, but will permit the current to go from the charge side through this charging Mosfet switch, let's say, through the diode that's inside the Mosfets. So the Mosfets, even if they are turned off and don't permit passing current from this side to this side, the diode will permit the passing to the current for charging the batteries. All the current is sensed by the air sense in one way and in the other way around, and that's it. The schematics for this one, it's normally like this, with only one port that does only one connection to the BMS that does the charging and the discharging, and you have only one wire. But there is the possibility to connect the P, here they put it on the board, when you have separate ports, and you'll have a charging port and a discharging port. And that's an integrated, let's say, BMS system. This one in the picture, it's the BMS from a well-known battery producer. They sell it as drop-ins. And let's say the only couple of things that I like about this. First of all, they solder proper terminals, screw terminals on the PCB. That way you can go with a proper connection to the cable with a crimped connector and so on. And the second one, they installed the MOSFETs on the right way around, and they are on a dissipator, on a heat dissipator, in a proper way. The things I don't like, they used the cheap pieces of wire as a shunt, and in this type of configuration you don't have much room for calibration. But the inner working, the real functioning of the BMS is, here you have the balancing part. That's the same thing with a small chip, a transistor and a resistor that dissipates a bit of power. This is the balancing part of the battery, and this is the BMS part with the small chips with the double transistors, as the way we've seen on the other one. And they added a temperature sensor for the MOSFET part on the radiator and the temperature control for the other one. You can find the pictures online, and this one, it's out from a Reliant battery, let's say names. You can find the pictures online. This is like the whole thing closed, the ink was finishing in the printer. This is the other side of the BMS, and they used a couple of copper bars to give a little bit more power handling on the circuit. And that's the cheapest. This is the picture from the battery. It's with the wrong colors, but that's inside. It's is that battery that I was talking about. Now, after we saw two of the kinds of circuits that are using around, I have this Chinese cheap BMS that in theory it has a common port, only a common port where you can connect the load and the charge part. It has the balancing that it's sensing the voltage on every cell. It has the NTC, that's the temperature sensor. This one it's like for a e-bike born and then modified to have it like 120 amp capability. It has the UART where you can attach a Bluetooth or a computer, an RS485 communication where you can put a display or commands or so on, a CAN bus. And it has another connector that's not populated. I don't know what it used to be for, but since some version of these ones have a separate relay command, I think that can even be, seeing the diodes that are connected over here, can be for controlling an external relay instead of using the Mosfet switching. Now, between those two BMSs, those two systems, and this one, this is a step further. On my other video on the Torquedo battery, you can see the same chip. It's the BQ76930. In this case is the BQ7920. That it's reading the voltage from every cell. It has an output for the balancing also. It has the temperature sensing capability. It has a much better current sensing capability, and the most important of all, can be calibrated in software inside the chip. Then it has an output part that it's commanding the charging and discharging MOSFET. The charging is always the one that stays towards, let's say, in the series on the outside part. And the difference between this one and the other one is that here it has, parallel with the discharging MOSFET, the load MOSFETs, a big group of power diodes, a really big group of diodes that increase the power handling capacity, because it's not relying only on the internal diode that the MOSFETs have inside, but they put bigger diodes on the outside. In this way, whenever you have a discharge from the battery and the battery is in protection for under voltage, this will be closed, will not permit the passage of the current from the battery outside, but will permit the current to go in and continue charging. This thing permits, this is some kind of data sheet they give you, a constant 100 amp charge current and a discharge current of 120 amps. The 120 for discharge, it's a number that's a little bit high for from what I'm seeing over here, but the charging can even go. The difference between this one and other ones is that they have an MCU that's a microcontroller, and on this board you'll find an ST32, a proper low power microcontroller that it's communicating with the BMS chip, and it's handling the programming part of the chip, because this chip, it's, let's say, almost universal. You can use it for lithium ion, you can use it with lithium iron phosphate batteries, but depending on how you program the small circuit with the microcontroller from a computer, depending on how you program it, you can change the values. Everything is programmable. The part that it's laughable and it's a laughing part, it's the balancing. It's only 50 milliamp balancing, but for all the other functions that are inside this one, I'm more interested on the other functions than the balancing part of the circuit. It has a proper temperature sensor. That's the battery one, and then on the board it has a second temperature sensor that is reading the MOSFET temperature. It has proper calibrated shunt resistors, and there are 5 on one side and another 5 on the other side. They also used a bit of brass power handling of the circuit, although honestly I don't know if I would pull 120 amps through these transistors. Although the datasheet of the transistor is looking really good, but it's a Chinese one, also by a Chinese manufacturer, so all the numbers are just, I don't know if I trust them completely. Let's say the difference, to explain to a couple of people that might not know, the difference between a pulsed current, a MOSFET, you may see 1116 amp in the pulse current at 25 degree. Pulse, it's like a signal that it goes on and off, a lot of pulses, and that's the proper way to command the MOSFET. But they also work in a linear way, and then the current capability is going down. I don't trust me for the life of me that this could hold 314 amp at 25 degrees, not even for the terminals. They're really thin for that big power that they say. So I was telling, I don't know if I would pull 120 amp through this MOSFET, but I think that has a niche on the market, on the do-it-yourself batteries. Another particular thing you'll find on this board, it's a hard analog wired protection. You have the software protection that's programmable through the microcontroller to the chip, but then you have an analog protection. I don't know exactly, I didn't do the reverse engineering, but it has an analog protection at over voltage, under voltage, and so on. So this is, and over current, I think that is also. if the software part, the microcontroller gets stuck, if the BMS chip is getting blocked, stuck in software and so on, there is an analog part that is pulling down a protection on the circuit. The thing I would have preferred is that in these terminals would have been like proper terminals for screwing, like the other one have, this type of terminal that you can bolt a screw on and weld it. And I would have like the Mosfets on the proper dissipator. This is from a motor controller that I took out because I wanted to see what's inside and what failed. I even recovered a couple of Mosfets in the day I didn't have them in house. The printed circuit board, it's really thick as a copper, is really thick, and then it's glued in some way directly on the aluminum part, and the aluminum part goes over a big radiator for cooling purposes, and you have the big bolt connections done on the PCB. This one is insulated, for example. You don't have it on the other side. There are proper distancing, like social distancing these days, between the Mosfets on the H bridge. There are 3 of them in parallel for every side. This is the way I would have preferred to have the Mosfets installed for proper cooling. Now the point is, where one could use one of these. Certainly, if you want to draw big power, like in the most Victron, when you see a big power inverter that's connected on the lithium and everything is really high power systems and so on, you cannot use it as a central BMS and they'll command everything. In 60-70 amp, I don't think that will hit so much, and the power over the terminals, over the wire, I don't think will make them hit so much. After 80 amps, I think they will really hit. I didn't start testing with big power yet. You could use that, yes, if you have 3, 4, 5 of them in parallel. The other possible solution could be where you have a small boat, or when you use the lithium phosphate battery with cheap elements like the blue prismatic ones. This is a picture from the internet. I don't know who did it. It's laminated on the battery, and even if you have like 120 amp cells, that's 120 amp maximum current, you could limit electronically from the menu, and you can limit the current. At this point, using one of these for the chip cells and make your own battery and do 2 or 3 of them in parallel could be one solution. Could be one of the cases where you can use it if you don't use big powers. Now I have the data sheet of one cell. Let's say if you are using the Winston cells that are rated continuous 0.5 C discharge, optimal discharge, so using on 50 amp but will hold 300 amps, so this one you can use them like in 1C. If you have this one and you want to use them with big power draw, is not indicated if you want to have big loads over it. But if you are using the cheap aluminum cells that are born for 0.2 C standard charging and maximum discharging 1C, but you keep them like 0.2, 0.3, so use them on board only like the old lead acid or gel or AGM batteries. In that case, it might have his own market. You can even slam it on a pack of 200 amp hour cells, limit let's say at 80 amp the charging current and the discharging current, and the overprotection let's say at 90 amp, and in that case I think you can get away with it. In fact, I will try it on board. If you have a small boat like 30 foot, 35 feet and so on, where the biggest draw it's a 500 watt anchor windlass, or I don't know, 70 amp anchor windlass, I think you can get away with using one of these.